Convexity. So this is actually a very important property, which uses the algebraic structure of the commodity space, the ability to speak of the sum of two bundles and the multiplication of a bundle by a scalar. So roughly speaking, what's the idea? The preference relation is convex if the upper contour set is convex. So let's write this formally for all commodity bundles in the space. The upper contour set, which is the set of all points in the commodity space such that these bundles are at least as good as X. Okay, that's a set. That's the upper contour set. That must be convex. What does it mean for a set to be convex? If I pick 2 points that are in the set, their linear combination must also be in the set. So let's just apply that. The preference relation is convex if, for all y, which is at least as good as x, and for all z, at least as good as x, right? I pick 2 points that are in the upper contour set. They're at least as good as x. The linear combination, so I need alpha, which is a number between 0 and 1. The linear combination between these 2 points must also be in the upper contour set, so it must be at least as good as x. That is the requirement here. So I have to be able, right, to add commodity bundles, and I have to be able to multiply them by a scalar, right? And I have to be able to add them. And then test whether or not the resulting bundle is at least as good as x. Let me draw this graphically, just so you can see. Okay, here's commodity 1, commodity 2, here is my bundle x. And let me show you the indifferent surface, which is like this. I pick, so this is the upper contour set. Let me change color here, right? This is the upper contour set. Let me pick 2 points, y and z in that set. So here is y, here is z. I'm picking z directly on the indifference surface, but it doesn't matter. It could be anywhere in the upper contour set. Their linear combination here is in the upper contour set. Where I'm at here depends on what value I choose for alpha. If I pick alpha equal 2.5, I'm going to be halfway through here. This is my linear combination, and it must be at least as good as x. What would a non-convex upper contour set look like? Well, depending on the shape of my indifference surface, if my indifference surface was something like this, for example, okay, and here is my upper contour set, all right, all here. I can pick y and z. Let me pick, for example, y to be here, and let me pick z here. All right, I do have y at least as good as x, it's on the indifferent surface. I have z at least as good as x, it's on the indifferent surface, but I find that their linear combination here is not included in the upper contour set. So let's repeat this for a second here. What we're saying is that a preference relation is convex if for all x in the commodity space, the upper contour set, which are all those elements in the commodity space, which are such that those elements, those bundles, are at least as good as x, right? That upper contour set is convex. What I want to try to explain to you here is that this is the same thing as saying that the utility function is quasi-concave. this is a little bit tricky because we have the word convex on the one hand and the word quasi-concave or concave on the other hand. Now the definition for a function is quasi-concave. Function u is quasi-concave if it's mapping from a domain x into R, right? And the upper contour set, which are x element of the commodity space such that u of x is greater than some value, some level, let's call it u bar, that set must be convex. That's the definition of a quasi-concave utility function. Now, by the way, if I was speaking of convexity here, the definition of a quasi-convex function is the exact same thing, except I'm looking at the lower contour set and not the upper contour set. Now, to put it another way, what I'm doing with that first definition up here is what I'm saying is that for all x element of the commodity space, I'm looking at all those other bundles out there which are such that the utility of y is greater than or equal to the utility of x. And I'm saying that this upper contour set must be convex. Therefore, the utility function is quasi-concave because I'm looking at the upper contour set, not the lower contour set, right? Otherwise, the utility function would be quasi-convex. Let me show you a graphical representation of this, just to be crystal clear. But what I want to say here is what I've done is I've simply picked my u bar here to be the utility associated with a particular bundle x, right? And I'm looking at all those other bundles out there which are such that the utility is greater than this level, and that the set of all those bundles must be convex, right? Upper contour set is convex, and that's the same thing as the utility function being quasi-concave. So the graphical representation, okay, so here I am. Here's my commodity space, x, and here I'm looking at the utility function. Utility function might look something like this. Okay, this function here is, the utility function is said to be quasi-concave if for any bundle x that I've picked, and I set a level, a particular utility level, okay, which is going to be this, for example. This utility level is the utility of a bundle, x, u of x. And now I'm looking at, in the domain, all the bundles which are such that they have a utility which is greater than or equal to u of x. Where are those bundles located? And I'm looking here, down here, I'm looking at the domain for the function. Bundles are going to be located in here, right? This is the set. Let me write it down. This is the set of y in the commodity space such that u of y is greater than or equal to u of x. And let me maybe draw this, show you in a different color. Here is the set. And I can check that, you know, any bundle here in that set, for example, this bundle, where is the utility? It's going to be up here. And indeed, the utility is going to be greater than or equal to the u of x. Other bundles, for example, a bundle here, that is not the case, right? And I can easily see that the utility would be here, and that would be lower than u of x. What makes the utility function quasi-concave is simply the requirement that the set here be a convex set. Is this convex? Yes. Why? because I can pick any 2 points in that set, their linear combination will also be in the set. Can I give you an example of a utility function that would fail this requirement? Yes. Oops, sorry, let me change color. Utility function that might look something like this. Okay, this is a very strange shape indeed, but I can pick a level. Here is u of x, and the upper contour set would be as follows. Would be this here, and would be this here, right? It is the case indeed that the utility of any bundle in that set is greater than or equal to this level, and same here, any bundle in that set, the utility is greater than or equal to u of x. The upper contour set consists of those two sets, here and here, and that is not a convex set. Why not? Because I could pick a point, a bundle, I could pick a bundle in the first set here, another bundle in the set here. Those 2 points are both in the upper contour set, but their linear combination, for example, some point halfway through, that would be here, would not, right? It would fall outside of the upper contour set. Therefore, this function, this utility function here that I have drawn, right? This is the utility function. This function is not quasi-concave. So what I've told you is that I've shown you a utility function that looked something like this. Maybe like this, okay? And I told you that this utility function was quasi-concave because the upper contour set was convex. As it turns out, the way that I've drawn this, the function is also concave. I want to explain to you the difference between the two. So the reason that this function, as it's currently drawn, is also concave is that if I take two bundles, x and x prime, so let me change color. Okay, here is x, and here is x prime. And here is u of x. Okay, and here is u of x prime. Okay. So if I take the linear combination of x and x prime, let me consider the following bundle. Let me change color. Alpha x plus 1 minus alpha x prime. Oops, sorry, start again. Alpha x plus 1 minus alpha x prime. This is simply the linear combination. It's going to be found somewhere on here, depending on the value that I pick for alpha. Alpha is a number between 0 and 1. Okay. Let's say, for example, I pick alpha equal to 0.5, so it's going to be found here. The utility of that combination bundle is up here, right? Okay. So the utility is this point here. Okay. Now the property of a concave function is that the utility of the linear combination of alpha x plus 1 minus alpha x prime is actually greater than or equal to the linear combination of the utility of x and the utility of x prime, which is going to be alpha u of x plus 1 minus alpha u of x prime. And that bundle is going to be somewhere between ux and u of x, and since I've picked alpha equal to 5, I am actually here, this point here. Okay, so this whole number here, this is found here. Okay, I'm trying to draw this. So that's the property of a concave function. For a convex function, it would be the same thing, except that we would be saying that the utility of alpha x plus 1 minus alpha x prime would be lesser than or equal to, okay, the linear combination of the utility of x and x prime. Okay. So let me show you here another example of what a utility function might look like if it were quasi-concave but not concave. So all functions that are concave are also quasi-concave. And I can check here, of course, if I was to check the level set, if I was going to check, for example, the set of y such that u of y is greater than u of x, or the set of x prime such that u of x prime is greater than or equal to u of x, I would find, you know, that that the upper contour set would be convex for the same reason as I've outlined before. So all concave functions are also quasi-concave. However, it's possible for a function to be quasi-concave and not be concave. Okay, and let me show you what that function might look like. So a function that looks something like this, for example. Okay, this function is quasi-concave. Why is it? Because I can simply pick a level, some utility level here, u of x, and I can look at the upper contour set, which is the set of y element of the domain, the commodity space x, such as u of y is greater than or equal to u of x. Okay. And where would this upper contour set be? It would be found right here. Okay, so this is the upper contour set. That set happens to be convex, so the function is indeed quasi-concave. However, the function is not concave, and it would be a little bit hard for me to draw it here, but I could show you, for example, that I could pick 2 points here, for example, x, all right, and x prime, and I could look at the utility of a linear combination bundle, which might be here, okay, all right. And as it turns out, this combination bundle would have a utility here that might be lower than the linear combination of u of x and u of x prime, okay, which would be found here, and that would be a little bit higher, perhaps. So this function is not concave, right, but it is quasi-concave. So this is a pretty central assumption in economics, pretty central hypothesis. It's also quite strong, plays a very key role, for example, in general equilibrium theory, in deriving some of the results. How do we justify that this assumption is not just desirable to make, but it's also justified? What's the intuition for it and the sort of the justification? Well, there are a number of interpretations. One has to do with the diminishing marginal rates of substitution between two commodities. So if I'm looking at here, commodity 1 and 2, here's a bundle X, and here's the indifference surface. If I'm compensating for the loss of 1 unit of commodity 2. Okay. How much do I have to add in terms of commodity 1 to bring myself back to the indifferent surface? Well, the idea is that this amount, because of the diminishing marginal rate of substitution, this amount keeps increasing. So now I'm reducing by 1 unit of commodity 2, and I have to add a little bit more than I did before to bring myself back to the indifferent surface. And now it's kind of clearer. You can really see that I have to increase by a huge amount to bring myself back to the indifferent surface. So that's one possible interpretation. Another interpretation is the idea that diversification is good. That if, for example, I pick 2 bundles that are indifferent to one another, let me pick another color so we can draw this. You know, X, for example, and this bundle here, Y, we have indifference. Well, if I'm indifferent between X and Y, there is no reason that I would not also be indifferent to a third bundle, which is the linear combination. Actually, I might be even better off through the combination, but I will never be worse off. So all of the possible bundles which can be formed by the combination of X and Y will be at least as good as either X or Y. So embedded into this is this sort of diversification interpretation in terms of behavior. You could think of it in terms of behavior under uncertainty even. Now, you know, one could easily think of situations where this is violated. For example, I may enjoy chocolate milk and I may be indifferent in terms of a snack between having chocolate milk or maybe having a little bit of sushi, right? But I may not want to be eating both of them at the same time. But you could always rescue yourself out of this type of argument by making the case that when we're looking at commodity bundles and amounts of commodities being consumed, that we're looking at amounts being consumed over time and not necessarily at a given point in time. So here, if I'm truly indifferent between chocolate milk and sushi, I might actually be able to make a case that I will that the combination, you know, having a little bit of sushi and a little bit of chocolate milk over time, that I will be at least as well off than if I were just eating only sushi or eating only chocolate milk over time.